Learn inspection permutation importance. Description. Explain in detail. Permutation importance is a technique used to assess the relative importance of features in a machine learning model by measuring how much the model's performance decreases when a specific feature is randomly shuffled or permuted. This method provides insights into which features contribute most significantly to the model's predictions. Inputs. Input 1. Explain in detail. Estimator, a trained machine learning model. This could be a classification or regression model, such as a random forest, logistic regression, or support vector machine. Input 2. Explain in detail. X, the dataset containing the features. Input 3. Explain in detail Y, the target variable or labels. Input 4. Explain in detail scoring, the scoring function used to evaluate the model's performance. Examples include accuracy, precision, recall, F1 score, mean squared error, etc. Input 5. Explain in detail. N repeats, the number of times the permutation process is repeated for each feature to obtain more robust results and estimate uncertainty. Input 6. Explain in detail. N jobs, the number of CPU cores to use for parallel processing, which can accelerate the permutation process. Input 7. Explain in detail. Random state, a seed value for the random number generator used during permutation. Input 8. Explain in detail. Refit, a Boolean flag indicating whether to refit the model on permuted data. This can be helpful for complex models where refitting may be necessary for accurate performance. Evaluation. Outputs. Output 1. Explain in detail. Importance, a pandas data frame containing the permutation importance scores for each feature. The scores indicate how much the model's performance drops when the feature is shuffled, providing a measure of its importance. Output 2. Explain in detail. Results, a dictionary containing the detailed results of permutation importance analysis for each feature. The dictionary includes the feature name, the mean importance score, the standard deviation of the scores, and the raw scores from each permutation. Steps. Step 1. Explain in detail. Shuffle feature for each feature. The values are randomly shuffled or permuted while keeping other features unchanged. Step 2. Explain in detail. Evaluate model. The model is evaluated using the scoring function on dataset with the permuted feature. Step 3. Explain in detail. Calculate importance. The difference between the model's performance on original data and the permuted data is calculated. This difference represents the importance of the permuted feature. Step 4. Explain in detail. Repeat process. Steps 1 to 3 are repeated multiple times for each feature to estimate the importance score and its variability. Metrics. Metric 1. Explain in detail. Mean importance, the average importance score across multiple permutations. Metric 2. Explain in detail. Standard deviation of importance, a measure of the variability of importance scores, indicating the uncertainty in the estimation. Visualization plots. Visualization plot 1. Explain in detail. Bar plot. A bar plot can be created to visualize the feature importance scores, allowing for easy comparison of the relative importance of different features. Visualization plot 2. Explain in detail. Box plot. A box plot can be used to illustrate the distribution of importance scores for each feature, providing insights into the variability and uncertainty. Fine-tune parameters. Parameter 1. Explain in detail. N repeats. Increasing the number of repetitions N repeats can provide more robust and stable importance scores, particularly for complex models or when there is high noise in the data. Parameter 2. Explain in detail. Scoring. Selecting an appropriate scoring metric. Scoring is crucial for interpreting the results correctly. Uncertainty methods. Uncertainty Method 1. Explain in detail standard deviation of importance. The standard deviation of the importance scores, calculated across multiple permutations, provides a measure of the uncertainty in the estimation of importance for each feature. Challenges and fixes. Challenge 1. Explain in detail high feature correlation if features are highly correlated. Permutation importance may not accurately reflect their individual contributions. The model may be using a combination of correlated features, and shuffling one feature may not have a significant impact on performance. Sample use case that resulted in Challenge 1. A model predicting house prices may have highly correlated features like square footage and number of bedrooms. Fixes to Challenge 1. Feature selection. Consider using feature selection methods, e.g., recursive feature elimination, to identify and remove redundant features before using permutation. Importance. Regularization techniques. Techniques like L1 regularization lasso can help to penalize models with many features, potentially reducing the impact of correlated features. Feature engineering. Combine highly correlated features into a single feature that captures their joint effect. Challenge 2. Explain in detail nonlinear relationships. Permutation importance may underestimate the importance of features involved in complex nonlinear relationships with the target variable. Sample use case that resulted in Challenge 2. A model predicting customer churn may have a nonlinear relationship between customer tenure and churn probability. Fixes to Challenge 2. Feature engineering. Create new features that capture nonlinear relationships. For instance, consider adding polynomial terms or interaction terms between features. Model selection. Choose models capable of capturing nonlinear relationships, such as random forests, gradient boosting machines, or neural networks. Use of Shapley values. Explore alternative methods like Shapley values, which are more sensitive to nonlinear interactions and provide a more accurate assessment of individual feature importance.